Since each individual electric field due to each individual charge is represented by vectors, the net electric field location due to these charges is simply calculated by adding each of the vectors together. So E net, which is the total electric field at a point, equals the summation, that's this sign right here. You add up all the different electric fields. So in this case, if you have n electric fields, the total E net is equal to E1 plus E2 plus E3, etc., all the way out to En. The direction of each electric field determines the sign used. So recall the electric field is KQ over R squared. Now we're not going to worry about the sign of the charge right up here. We're going to use a number line to help us determine which way it's acting. And that'll be clear when we do the problem following this slide. The previous section talked about how a net electric field can be found from several charges by point adding the contributions from each charge to the field. This section, which is optional, will cover the math behind that addition. Here we have three charges, Q1 at a point x equals -8. You can see the number line here, right? Here is the origin at point 0. And I have this Q1 here at -8, Q2 at -2, and Q3 at +4. And we want to find the electric field at the origin, and origin means where x equals 0. So the strategy. First thing, mark the point on the drawing where we want to calculate the electric field. So that would be right here, right at the origin. Next, you would draw the electric fields acting at that point. And this is what I said on the previous slide. Don't worry so much about the signs of the charges for the equation. We worry about it when we put it on the number line. For example, at this point, remember, we need a positive test charge. That's the direction of the electric field. What direction that positive test charge would move. So E1, which is the electric field due to Q1, would push the charge to the right. So you can see here E1 going to the right. E2, which is positive, would also push it to the right. So E2 over here would be to the right. Now here's where the issue comes in. Q3 is a positive charge, and the electric field will be going that direction and that direction. So if there's a positive test charge here, it's going to feel a force to the left. And here you have E3 going to the left. Now, the next step, we'll calculate E1, E2, and E3 using the equation E equals KQ over R squared. And if the field is pointing to the left, that's when we'll put a negative value in for E. If it's pointing to the right, like in the case of E1 and E2, we'll assign a positive value. And then you just combine the electric fields. You add them algebraically. So in this case, it would be E1 plus E2 minus E3. For our first attempt at this, we'll consider a simpler geometry here. We'll just have two charges, Q1, which is a positive charge at -8.0 meters, and it has a value of 9.1 microcoulombs. And remember, micro is 10 to the -6th, so this is plus 9.1 times 10 to the -6 coulombs. And then we have Q2 over here, which is a distance of 3 meters away from the origin. So the first step, we'll draw the electric fields acting on the origin right here at x equals 0. We'll find the magnitude and direction of the field first due to charge Q1, second due to charge Q2. Then we will add them together, and again it's a vector addition, so sign matters, and then we'll come up with the total electric field. The first step is to draw the electric fields acting at x equals 0. So what we have here is Q1's electric field is to the right, so at any point to the right of it, like here at the origin, its electric field would be to the right. Q2 would have an electric field going this way and also this way, so at this point the electric field would be going to the left, and that's this direction here, E2. The size of the vectors doesn't really matter for this drawing. What we really want to understand is the direction. This seems to indicate that E2 is a lot stronger because it's so much closer to the origin, but on the other hand, Q1 is a greater charge, so it has a greater electric field closer to it. So how they come out, which one is bigger, we'll find out when we do the calculation. Right now, all that's important is the direction. Find the magnitude and direction of the electric field at the origin due to charge Q1. So here's our equation. E1 is equal to kQ1 divided by r squared. Here's Coulomb's constant. Here's the value of Q1. Here's the distance. Notice, don't put -8 here, even though when you squared it, it would go away anyway. But the distance is 8. It's 8 meters away from the origin. And you come up with a number of 1.3 times 10 to the third newtons per coulomb. And again, the important part here is not only the magnitude, but to the direction. So we call it directed towards the right or the positive direction. Either answer would be good. Or you could draw an arrow. Anything that would make it clear to the reader. Next, find the magnitude and direction of the electric field at the origin due to charge Q2, this fellow right here. Once more, we use the definition of the electric field. E2 is equal to kQ2 over r squared, Coulomb's constant, the value of Q2, and how far away it is. In this case, it's only 3 meters. And notice here, there's no negative signs up here, but we're going to put one here because we know it's directed towards the left. So that's a negative electric field. It points to the left side, which is negative, and it's negative 3.0 times 10 to the third newtons per coulomb. So actually the electric field, the magnitude of this one is greater than Q1. Even though Q1 had a greater charge, it was further away from the point where we're calculating the electric field. And finally, find the net electric field. What we're going to do there is use the work we just found out. E net is equal to E1 plus E2. E1 was pointing to the right with the value of 1.3 times 10 to the third newtons per coulomb. And then E2 is contributing an electric field to the left, so it has a negative sign. Add those two together, and you get a negative 1.7 times 10 to the third newtons per coulomb, and the negative sign means the net electric field is directed towards the left. So you would represent that either by saying directed towards the left, you would have the negative sign, or you would draw a picture with E net going to the left.